Okay, next up we've got matrix multiplication in terms of columns and rows. Suppose I've got a product between two matrices and I'm only interested in a particular column or in a particular row of the product. Okay, so the jth column vector of A times B is simply the matrix A multiplied by the jth column vector of B. Okay, now let's just see how this works. Go back to our the two matrices A and B, which can be validly multiplied as the number of columns of A is the same as the number of rows of B. Okay, so then the jth column of A times B. How do we determine the jth column? So what we do is we take the first row of A and we dot it with the jth column of B, which is the column in blue. And that'll give us the first entry in the jth column of A times B. Then we dot the second row of A with the jth column of B. Then that's the second entry of the jth column of A times B. Then we run through until we get to the ith row of A, and if we dot that with the jth column of B, we get the ith entry in the jth column of A times B. Right, going through right up until the end, if we take the mth row of A and we dot that with the jth column of B, that is definitely going to give us the mth entry of the jth column of A times B. Okay. Going back there, if we're interested in the ith row of A times B, we basically just take the ith row vector of A and we multiply that with the matrix B. And why is that again? So take the ith row of A times B, and that is given by the ith row of A dotted with the whole of the matrix B. Okay, so you pinpoint the ith row of A, and then you run through all your columns of B. So how do we get the first entry of my ith row of A times B? You take the ith row of A and you dot it with the first column of B. That's the first entry. Then you move on to your second entry. You dot the ith row of A with the second column of B. Then you run through until you get the jth column of B, and you dot that with the ith row, and that is going to give me the jth entry of my ith row of A times B. Moving to the last column, we dot the ith row of A with the rth column of B, and that gives me the rth entry of my ith row of A times B. Okay, let's look at the following example to quickly establish that how this works. So you're given a matrix A and B, and you're asked to determine the second row of A times B and the third column of A times B. So let's look first at the second row of A times B. Okay, so the second row of A times B is given by the second row vector of A multiplied by the matrix B, and this is a normal matrix multiplication that we have to do. So basically the second row of A is going to be the row vector minus 1, 5, okay, and the matrix B is then the given 2 by 3 matrix. Okay, so establishing the size, our first matrix is a 1 by 2 matrix, the second one is a 2 by 3, so that is going to be a 1 by 3 matrix. So it is going to be a 1 by 3 matrix. We know what the dimensions of the matrix is going to be. Okay, so the first entry, you're going to take the first row of the first matrix and dot it with the first column. So that's going to be minus 1 times 4 plus 5 times 0, which is minus 4. Okay, then moving on to the second entry, the first row of the first matrix, dot it with the second column. So that's minus 1 times minus 2, which is 2, plus 5 times 2, which is 10. So the next entry is going to be 12. Okay. Then moving on to the next entry, it's the row vector dotted with the last column vector of b. So it's minus 1 times 1, which is minus 1, plus 5 times 3. Alright, so the third column of a times b is going to be a multiplied by the third column of b. Okay, so that's going to be the matrix A, which is this 2 by 2, 1. And you're going to dot that or multiply that with the third column of B. And the third column of B is that column vector. Okay, so first of all, this is a 2 by 2 multiplied by a 2 by 1. And so that is going to be a 2 by 1 matrix. Okay, it's going to be a 2 by 1 matrix. And so we know what the dimensions are. Okay, so that is going to be, so firstly, you are going to take the first, you're going to take the first row and you're going to dot that with the first column to get your first entry. That's going to be the entry in the first row and the first column. Okay, so dotting that, we get 3 times 1 plus 0, which is 3. And then you're going to move on to get your second entry, which is the entry in the second row and the first column. You're going to dot that with the second row of A with the first column of the matrix. So that's going to be minus 1 times 1 plus 5 times 3. So that's going to be 14. Okay. Now another way to look at the product again is if we partition B in terms of its column vectors. So B, the first column vector of B, you denote by B1 bar, B2 bar up until BR bar. Okay. And you go and write the product of A with B, then it's the same as the product of A with the partition matrix B, and you partition it into its column vectors. And then basically to get the first column vector of my product, it's going to be A multiplied by the first column, A multiplied by the second column up until the rth column. And that is going to give me my product. So if we were to consider this next example, right, if we look at A times B, okay, remember we take the matrix A and we multiply it with a partition matrix. And the partition matrix in this case is that matrix with a column vectors, right? So that is going to be that. The second column vector is going to be minus 2, 2. Okay. Right, and that is then going to be, the third column is going to be 1, 3. Okay, so that is going to be, you're going to multiply each vector with that, you're going to multiply the matrix A with each one of those vectors. Okay, I'm going to multiply A with the second one. You're going to multiply A with the last one. Now from the previous example, we already calculated A multiplied by the third column of B. Okay, so there we've got our final column there. And you guys can go and calculate A were multiplied by minus 2, 2 as an exercise, and that you should get minus 6, 12. Okay, and then A with 4, 0, that you should get 12 minus 4. Okay. Okay, and so basically you can just go and delete the brackets, and you will get your product of your matrix, your matrices. Okay. So you can basically view a product as in terms of partitions. Okay, now you can also do it alternatively by partitioning A into row vectors. Okay, so you partition A into row vectors, and then you can write the product of A times B. If you go back, we're basically going back to this section here where you calculate the ith row vector of A times B. So you partition A into its respective rows, and then calculating A times B, you basically multiply the matrix B with each one of the row vectors of A, and that will generate all the row vectors of the matrix A times B. Okay, so that will generate all the row vectors of the matrix A times B. Alright, so doing that, if we look at A times B, we can go and partition firstly A into its respective row vectors. So that's my first row vector there, 3, 0. Okay, and my second row vector is minus 1, 5. We already calculated one of them. You're going to multiply that with the matrix B. So that is going to be that's going to be 3, 0. You're going to multiply that with the whole vector B to get your first row, and you're going to multiply that with your second row. Okay. Okay, so there we've got our we're multiplying B with each one of the row vectors of A, and this matrix here, that is a 1 by 2, and you're multiplying it with B, which is 2 by 3. So that is going to be it's going to be a 1 by 3 matrix. Okay, it's going to be a 1 by 3. So, so working that out, we get what we have there in the notes. So you're going to get a vector. You're going to get a vector, a row vector, which is given by 12 minus 6 and 3. Okay, and then the second one as well, that is again, it is it's a 1 by 3 matrix, which is given by minus 4, 12, and 14. Okay, now you can then go and basically drop the brackets and get your actual matrix. Right, so you get your final product there. Okay, matrix products as linear combinations. So this is just an extra definition that we have to know. We're going to come across it a lot in this course, and that is the concept of linear combinations. So if A1 up until AR are all matrices of the same size, and if C1 up until CR are all scalars, then the sum of scalar multiples of these matrices, that is called a linear combination of the matrices A1, A2 up until AR. So that's a simple definition of a linear combination with regards to matrices. So there they just ask us, express this matrix as a linear combination of these two matrices. And now you just need to remember what you learned, how we multiplied a matrix with a scalar, and how we added matrices together, and when two matrices are the same. So it's going to be a little bit of a matrix equation that you're going to have to solve here. So let's look at that. Okay. So basically, what we want to do is let's C1, C2, be scalars such that we can express the matrix 5, 1, minus 1, minus 11. We can express that as a linear combination between the two matrices 1, 1, minus 1, 2. And this is a straightforward problem. Okay, so now you just need to solve. That matrix equation. Okay, so the right-hand side becomes basically scalar multiplication. So we know how that works. That's C1, C1 minus C1, 2C1. That's the one. And the other one is minus C2, C2, minus C2, and 5C2. Okay. Right, so you've got that equality, and then further simplification then yields the following. So that we have then adding the two matrices, we get C1 minus C2, we get C1 plus C2, we get minus C1 minus C2, and we get 2C1 plus 5C2. Okay. Right. Okay, so there we've got the two matrices equal to one another. So so that entry needs to be the same as that entry. So we need C1 minus C2 to be equal to 5. That's the one. Then we need this entry to be equal to that entry. So we need C1 plus C2 to be the same as minus 1. Okay. And then again, this entry here needs to be equal to that entry there. So again, we already have that equation. That needs to be 1. Okay, and the last one is minus 11 needs to be the same as 2C1 plus 5C2. Okay, so I mean these two equations are basically, they're the same. So so basically taking it from there, right, so we can add that to this. Okay, and what we do we need to take the right hand side into consideration as well. That is going to be equal to that. Okay, and so from there we can solve for C2. So that's minus 2C2 equal to 6. And from there we can solve for C2 as minus 3. Okay, so we've solved C2 as minus 3. And then plugging that back in, we get C1 minus C2, which is minus 3. Needs to be equal to 5, and from there we can solve for C1, and C1 is going to be 5 minus 3, which is 2. Okay, so we solved for C1 and C2. Okay, so C1, C2, they both satisfy that equation and that equation. And they also satisfy that equation. Let's just make sure that it satisfies that final equation there. Otherwise, there won't be a valid solution here. So we have that minus 11 should be equal to 2 times C1, which is 2, plus 5 times C2, which is minus 3. Okay, so hopefully those two things are the same. So that should be equal to 4 minus 15, which is going to be minus 11. Okay, so it satisfies that fourth equation as well. Okay, right. So that is clearly it's a valid solution. So to complete then the problem, we have that matrix on the left is basically C1, which we solved as 2. Okay, we take 2 and we replace C1 with 2, and then C2 we can replace with minus 3. Okay, so basically you take minus 3 there, and you replace that term with minus 3. Okay, so the matrix on the left is a linear combination of the two matrices 1, 1, minus 1, 2, and minus 1, 1, minus 1, 5. Okay, next up we've got theorem 1.3.1, which just says the following. Okay, next up we've got theorem 1.3.1, which just says the following. If A is an n by n matrix, and if X is an n by 1 column vector. Okay, so what is, if you take an n by n matrix and you multiply that with an n by 1 column vector, you are going to get a n by 1 matrix, right, which again is a matrix with m rows and 1 column. So it's again going to be a column matrix, right? Then AX bar, which is an n by 1 column matrix, is going to be a linear combination of the columns of A in which the coefficients are the entries of X. Okay, so if you take AX and you multiply, and you write that out and you multiply it with a column vector, then the columns of the matrix A, you can basically write this whole product as a linear combination of the column vectors of A, and the coefficients are the entries from the column vector that you're multiplying, which in this case is X. Now, to understand this, it's very, very straightforward. I'm just going to go in a little bit more depth. If you take a product between two matrices, A and B, and let's say I want to look at the jth column of the product of A and B, then maybe if I can express that column vector as a linear combination of the column vectors of A, then that will then this theorem will make a lot of sense. So let's go and look at that. Okay, so I want to look at quickly an illustration of this. Why is it that I can represent the column of the product between A and B as a linear combination of the column vectors of the matrix A? So I'm going to look at the product of A with B. Now we can multiply A and B together because the number of columns of A is the same as the number of rows of B. So let's look at a column vector of A times B. I'm going to look at the jth column vector of A times B. Now we basically said that this can be expressed as the matrix A that I'm going to multiply with the jth column of B, the jth column being the encircled blue column of B. Okay, so you take the first row of A and you dot it with the jth column of B. That's the first entry of the jth column of A times B. Then you take the second row of A and you dot it with the jth column. Go up until the ith row and dot it with the jth column. And then you take the last row of A, and you dot it with the jth column. That will give you your last entry in the jth column of A times B. So let's just partition A in terms of row vectors, and let's take A times the jth column of B. The jth column of B will denote by Cj. Okay, there is that column there. We denote that whole column by Cj, as I said. All right, then going back, because Cj is a column vector and each R is a row vector, we're going to dot Cj with each row vector. So we can replace A times jth column of B with R1.Cj, R2.Cj up until Rm.Cj. Okay, so note that Cj is an n by 1 matrix. It's got n rows and 1 column. Okay, so taking that into account, if we look at A is an n by n matrix. So let's just look at the size of that, just for interest's sake. If you that's going to be an n by 1. That's going to be an n by 1 column vector. Okay, so now let's look at the dot product R1 dot with Cj. So you take the the first row of A, and you're going to dot it with the jth column of B, which is basically Cj, and that is the whole column Cj. Now we know how to work that dot product out. Take the first entry there, multiply it with the first entry in the second vector, which is that entry there, and then we're going to add that to. We take the second entry in the row vector, we multiply it with the second entry in the column vector. Right. Okay. And then we carry the process through right up until the end. We multiply the last entry in the row vector with the last entry in the column vector. Okay, so that is my dot product. Okay, and that's my first entry in my column vector. Then I'm going to do the same. I'm going to do the same for the entry in the second row, and that's just the second row of A dotted with Cj. Okay, so there's the second row of A, and we're going to dot that with Cj. Okay, again, take the first entry of your row vector, multiply that with the first entry in your column vector, which is B1j. Okay, so we have to take that and multiply it. Then we get to that, we're going to add. We're going to take the second entry of the row vector and multiply that with a second entry in the column vector, which is B2j. Okay, and we're going to carry this process through right up until the end, until we get to the last entry in the row vector. That's going to be A2n, and we're going to multiply that with the last entry in the column vector, which is B subscript nj. Okay, so that is the expression of, well, that's the value of my second row. So replacing the second row with that expression, we get there that whole sum there. And we can carry this process through until we get to the ith row. So it's the ith row of A dotted with Cj. So again, it's the ith row of A dotted with Cj. And again, we match the entries, and we multiply each entry with its partner, with its matching partner. And then we run through right up until the end. We take the mth row and we dot it with the column CJ, so the mth row dotted with that, it gives me that whole expression, and we plug it in there. Okay, so now I've worked out this column vector, and this is a column vector from the product A times B. Okay, now we are going to simplify that product. We're going to simplify that column vector. So we can do it by writing that column vector as a sum between separate column vectors. Okay, so let's separate the first all the first terms of the rows, and let's throw them into a column vector. Okay, take all the second terms, throw them into a column vector, and we carry this process through right up until the end. We look at the last group of expressions, we group them all together, and we put them all in a column vector. Okay, so that's a sum between column vectors. Then taking and replacing the left-hand side with the right-hand side, which is the sum of the column vectors, we can easily see that that again is a sum between column vectors. So we can take that expression on its own and modify it slightly. You can see in that first column vector there's a common scalar term in each of the rows, which is the scalar being B1J. Okay, so we can take that out, and that becomes a single scalar that we multiply with the first column vector. Okay, then we take the second column vector, and what we do is we again notice that there's a scalar multiple in this second column vector, the scalar multiple being B2J. So we can take that B2J term out from every single row, and that forms another scalar multiple. Okay, and we carry this process through until we get to the last column. So the last column has got another scalar multiple, which is in this case BNJ. So we can take BNJ out, and we form another scalar multiple of a column vector. Okay. Right, now if we look at these coefficients, we see that they are actually the B's. They are the coefficients come from the column vector that we are looking at, which is CJ. Okay, so that's an important point to remember, especially with regards to the previous theorem we talked about. Right, so as I said, that's a linear combination. So we established equality there. So that is a linear combination because it's of the form, it's got vectors, and it's a sum of scalar multiples of these vectors. Okay, so what are the actual vectors? Where do these vectors come from? Go back to my matrix A, right? There's my matrix A, and I'm just going to draw a circle, a rectangle around that. If you were to compare the vectors that we have here, right? So there, that is the first column vector of that matrix. That is the second column vector, that matrix. And that's the last column vector. Okay, so what have we written down here? We have established that this column vector is in fact a linear combination of the column vectors of the matrix A. It's a linear combination of the column matrices of the matrix A. So you can always write a product between two matrices A and B. You can always write the column, each column of that product. you can write as a linear combination of the column vectors of the matrix that occurs first in the product. Okay, so going back to this theorem, again, we just showed that if you take the product of A with a column vector, right, then we showed that you can basically, the column vector that you get by multiplying A with X, that is a linear combination of these column vectors of A, and the coefficients come from this column vector that you're multiplying the matrix A with. Remember, we took Cj from the matrix B, and that was my column vector, and we multiplied that with the whole matrix A. So we dotted that vector with every row vector of A, and then we constructed that matrix and we broke it up into a sum of scalar multiples, and those coefficients were basically the values that came from that column vector. So my previous illustration illustrates this theorem very, very well. So it's the same argument. Okay, and so it follows on here that we can write the columns of A times B as a linear combination of the columns of A. And we just illustrated that as well. We took a column from A times B, and that was a particular column, and we took we showed that column matrix that we obtained, and the column matrix that we obtained in this case was, remember, we took A and we multiplied A with, we dotted A with Cj. So A had all the rows, right? Okay. And then we took the jth column of B. We took the jth column of B. So we took this expression here, and we took the dot product with Cj, which was the jth column of B. And Cj you dot with each one of the rows. Okay, and that is this dot product is a particular column, that's a column vector from the matrix A times B. Okay, so any column vector of the product of A and B can be expressed in this particular form. And then we showed that matrix can be broken up as a linear combination between the column vectors of A. And again, the coefficients that we talked about, they all come from the vector Cj. Okay, and so by the previous theorem, if you take A and B and you look at A times B, you can always take B and partition it into columns, and then you multiply the matrix with each one of the columns to get your basic columns of A times B. And calculating it separately, we see that the matrix A multiplied by this column, remember in the previous illustration we showed that if you multiply the matrix A with a column, it's the same as dotting. It's the same as dotting each row with this column vector here. Then we showed that that is a linear combination of the actual columns of A, and the coefficients come from this particular column vector. And the same story holds true for this one here. Again, by the previous theorem, you can express that as a linear combination of the vectors, the column vectors of A, and the coefficients come from there. Okay, then again the last one, there you multiply again the you dot each one of the rows by that, and we showed that that is simply just merely taking the column vectors and looking at this particular linear combination where the coefficients come from there. Okay, so that is just an illustration of the previous theorem. Okay, then just the matrix form of a linear system. If you're given a linear system of equations, remember then you can write down the augmented matrix. But the augmented matrix you can also write it in this form, where you can write it in the form AX equals B, where B is a column vector, and it's the column vector formed by those entries there. X is again also a column vector, right? And the matrix A is just formed by the coefficients of the coefficients of all the terms. Okay, so the coefficients of the first linear system, they are going to form your first row. The coefficients from the second linear system, that's going to form my second row up until the mth row. Okay, so that's just a different way of writing a linear system. That's the augmented matrix form that we're already familiar with, which is basically just this form here. So please just take note of that. Then a concept that we will talk about a little bit as well in this course is the transpose of a matrix. So a transpose is an operation on a matrix, and I'll describe to you just now what the operation is. So transpose of an m by n matrix A is pretty much an n by m matrix, and it's denoted by a T. And it's basically obtained by interchanging the rows and the columns of A. So that is, the ith column of AT is the ith row of A for all I. And so basically you can denote, if A is a matrix and its general entry is given by I subscript J. Remember, I subscript J stands for the entry in the ith row in the jth column of A. Then the transpose, okay, let's look at A's transpose again. So to get a better idea of what A's transpose looks like, we look at the entry in the ith row in the jth column. Okay. Now, if we look at A, if we look at the definition of A's transpose, what is the entry of A that gets sent under the transpose to the entry in the ith row in the jth column? Okay, so what entry is at play here in the matrix A? So if we look at the ith column, so if we look at the ith column of A, and we look at the jth row of A. So there's the jth row of A. So that is the jth row of A. If we look at that entry there, what is the entry there? It's the entry that lies in the jth row and the ith column of A. Okay. Now under the transpose, where does that entry get sent to? Under the transpose. Okay. Now under the transpose, what happens to the ith column? What happens to the ith column? The ith column becomes my ith row. Okay, that becomes my ith row of A's transpose. So we're working with A's transpose now. And what happens to the jth row of A? The jth row of A becomes the jth column of A's transpose. Okay, so that entry there is going to be the entry that is going to be in the transpose of A, and it's going to lie in the ith row of A's transpose, and that is going to lie in the jth column of A's transpose. Okay, so the A's transpose, you can basically write the entry in the ith row in the jth column of that is going to be this entry here, which is A subscript ji, and that's the entry in the matrix A that lies in the jth row and the ith column of A. Okay, looking at the examples, what is A's transpose? That very simply is 2 minus 1, 4, 1, 0, minus 2, 0, 2, 7, and 3, 4, 0. Okay, looking at the other one, let's look at C. So C's transpose, again, that's row, so that is going to become a column. Okay, and then lastly, B is going to be, again, the same story. So that is going to be 4, 0, minus 2, 2, and 1, 3. Okay, lastly, we've got the trace of a matrix. Just take note of this definition as well. It only applies to a square matrix, and we say the trace of A, denoted by TR of A, is just the sum of the entries on the main diagonal. Now, the diagonal entries are all the entries in a matrix A, the square matrix A, where the indices are the same. Okay, the row index is the same as the column index. So that's an entry on the diagonal. It lies in the ith row and the ith column. So the trace of this matrix is simply just going to be the sum of the entries on the main diagonal. Okay, so calculating that, you will then have 9 plus 1 plus 5, which is 15. Okay. And if A is not a square, the trace of A is undefined. So the trace is a parameter of a matrix, and as we go through the semester, you'll see that the trace has some uses.